We present the splatter image, a method for ultra-fast single-view 3D reconstruction. Splatter image outputs a 3D shape from just a single input image.
Our method is very fast. The reconstruction is obtained from a single forward pass through a 2D network. We leverage 3D Gaussians as the underlying 3D representation, thus the output can be rendered with Gaussian splatting. Splatter Image achieves state-of-the-art quality in several cases, is cheap to train, performs reconstruction in the camera view space, and can be extended to multi-view reconstruction.
Splatter image works by passing an input image to an image-to-image network, which outputs another image, the splatter image. Each pixel in the splatter image holds parameters of one 3D Gaussian. Thus, the splatter image represents a 3D shape which can be rendered with Gaussian splatting. Notably, despite having the structure of an image, the splatter image represents full 360 degrees of an object.
Full 360-degree prediction is achieved with the parametrization of position prediction. The network predicts monocular depth for each pixel, which allows for representing high-frequency visual detail of the visible parts. In addition, the network predicts a three-dimensional offset, which allows the Gaussians to be placed at unconstrained 3D locations, including in the occluded regions of the object.
The reconstruction network is trained by rendering the 3D shape represented by the splatter image from a target camera. The network is trained by optimizing the losses applied on an image level, including the L2 loss. Since rendering is very fast, we can render full images, which allows using perceptual losses in optimization too. Splatter image can be extended to perform multi-view reconstruction by performing reconstruction in each of the input views with a cross-view attention mechanism and providing information about the relative camera pose. The output point clouds can be warped to a common reference frame and concatenated to form the final reconstruction.
The splatter image outputs reconstructions which are more accurate and sharper than baseline methods, while rendering 3 orders of magnitude faster.
Here, we present the comparison to the commonly used baseline pixel nerve on real data from the challenging Co3D dataset. Here we present the reconstructions output by our method on a variety of objects.
The splatter image can represent complete 3D shapes with appropriately predicted offsets in non-foreground pixels to reconstruct the occluded object parts, for example, the car wheel or the chair leg. Alternatively, it can allocate some of the foreground pixels to the non-visible object parts.
Finally, we measure the speed efficiency of our method. First, we evaluate the test time efficiency by measuring how long it takes to reconstruct a single object and render 250 views, which is what is required to test the method on the standard ShapeNet benchmark. Our method is 1,000 times faster, where PixelNerve needs 45 GPU hours to evaluate on the ShapeNet car validation set. Ours only needs 10 minutes. In training, one does not need to render 250 views, so we measure the train time efficiency by measuring the time needed to render 4 views of an object. Again, our method is much faster than the baselines. We also include results from other methods, but since the code is not available online, we're not able to reproduce these results and include them in brackets.
This translates directly to the low training cost of our method. Our method only needs a single GPU to train and is significantly cheaper than some alternatives. Thank you for listening.